All right, today we're taking a look at section 7.6. And 7.6 is going to start out kind of like what happened in a lot of chapter 5, where we did some algebra or trig stuff first, and then we moved into the calculus component of what we were talking about. Y'all remember that? It's going to feel like that. So we're going to start by talking about, for those of you who are in engineering and physics and stuff like that, these are all very familiar sciencey kind of topics. We're going to talk about mass. All right, so mass is a measure of a body's resistance to change in motion. It's independent of the gravitational system you're in. Sometimes we equate this with weight, though that's not technically correct, which you probably know that. This is a type of force, and it's related by the equation. Force equals mass times what? Y'all know it? Acceleration. I think there's only one L. Acceleration. I'm not 100% sure that this is page 494, although in my notes it says 498, so it probably is 494 if you were to go and look at it. Yours says 486, so I didn't get this one changed. Excellent. 486 sounds good. There's been an addition change since I had written it in there originally. So there are some commonly used measures for mass on there and their conversion factors. You may need them, you may not, but they're there if you need them. What we're going to talk about is we're going to talk about something called moments. So this is, we're generally going to talk about what's called center of gravity or center of mass. The first thing we need to do that is we're going to talk about moment of mass. So a moment of mass is a measure of a body's resistance, object's ability to resist rotational change. I feel like that's not written quite right. Object's ability to resist rotational change. Let's go like that. A measure of an object's ability to resist rotational change. It depends on the mass of the object and its distance from where the object is being moved. So in general, sort of generically speaking, the moment is figured or calculated by taking your mass times the length of the moment arm otherwise known as the distance to the fulcrum. And I'm not sure. I'm not going to answer you yes or no because I don't know as much about physics as y'all do without question, so I don't know. But what I want you to do, let's see, how do we have 2, 4, 6? I want you to split into 3 groups, okay? You're going to stand up, and everybody needs one of these, okay? Actually, let me do one example before we get to that because it's better fit with our second example. So we're going to need one of these in a second. Okay, so the first example I'm going to do, I'm just going to draw a picture of it because I don't want to bring in a 600-pound rock. That's why, really, okay? All right, so we're going to consider a person weighing 200 pounds sitting on one end of a 5-foot-long beam. So the picture you want to have in your mind is a teeter-totter. You know what I mean when I say teeter-totter? Right, the thing that the children play on the playgrounds, you know, and they go like this. They go back and forth depending on the weight of the child. Okay, good. So you want to have that sort of picture where the 200-pound man is on one side and there's a rock that weighs 600 pounds on the other side. And you're wanting to lift the rock off the ground, and that's probably not a wise thing to do just with your own strength. Agreed? Yeah, we're not going to do it that way. So we have this beam. The beam, it tells us, is that it's 5 feet long. We have our person on one side, and I do recognize that 200 pounds is not his mass, but for the purposes of what we're doing, it will work okay to use it as though it were mass, okay? I get that. And we have our rock. Our rock is over here, and our rock is 600 pounds. Okay, so somewhere in between the man and the rock, there is a location, and that location is what we're calling the fulcrum. Okay, it's the center part of a teeter-totter. So like on a teeter-totter, it's just halfway in between. But the goal, what we're going to be working on, is trying to find the location where it would balance the teeter-totter. Are you with me? Clearly, the 600-pound man, or the 600-pound rock, and the 200-pound man are not balanced if the center is actually in between, like exactly in the middle, right? Like, that wouldn't work. Okay? So it's got to be closer to one side or the other to get the balance right so that they're actually in balance with one another. Can you picture what I'm describing? Okay, good. So we have, let me write it down here first. Force is mass times acceleration. That's the only formula I've given you so far, pretty much, right? And then we have this one here about the moment. There's one more I did give you. The moment, excuse me, our moment is mass times the distance x. So this force right here, mass times acceleration, is my 200 pounds and my 600 pounds. Okay, that's my force. That's the force due to gravity. Right? We each have a mass, and our mass due to our gravity on Earth is going to give us our weight. So these are actually forces, right? These is kind of like working with forces. Okay, so here's our people, or here's our image. And one of these distances, and it doesn't matter which one you use it as, but one of these distances is x. So what would the other one be? 5 minus x. This looks like something we just did on a quiz, right? Keeps coming back. It's going to come back frequently enough, you're going to be like, I can see that now, right? X and 5 minus x. So we have the mass of we've got the weight, our 200-pound man. And this is backwards of how it's written on my paper, but that's okay. So the 200-pound man, oh no, it's not, has a distance that is x from the fulcrum, right? His weight, his distance. And then my 600-pound rock has a distance 5 minus x from the fulcrum. And what we want is we want these to be balanced, which is why they're going to be set equal to one another. Our goal is to find the location where we would place the fulcrum. Okay? So this is in calculus, right? One of my children was sitting next to me as I was preparing my lesson last night, and she was like, Mom, I know how to do that. She's in 9th grade. They're working with equations. It looked familiar to her, right? Yeah, because it's algebra. Yeah, so it's algebra. So we're going to simplify this. So this is 200x equals... This would be 3,000 minus 600x. We'll add our 600x to both sides. So we have 800x equals 3,000. If I divide by 800, what is my x?
15 over 4.
Okay, can we turn it into a decimal? It'll make more sense for our context. 3.75. It's 3.75. There are units. 3.75 what? Feet. And because I've got two distances, I think it was feet, wasn't it? Yeah. Okay. Because I've got two distances I'm measuring, descriptively, I would like to say where this is locating. It's 3.75 feet from what? From the person, right? 75 feet from our person. So if somebody else had set up this problem differently, where you put the x as the distance between the rock and the fulcrum, right? And the 5 minus x between the person and the fulcrum, your x would turn out to be a different value because you've defined x differently. But then in this description at the end, you would say that it's the distance from the rock. Does that make sense? Now, WebAssign may tell you what they want the distance to be from to sort of keep that from happening. But just to be aware that in a real true sense, like that is another possible answer that would be equal to what we've got. All good? Okay, so let me preface what we're going to do for our activity. We can generalize this idea to multiple weights along a line. Okay, so we've got our beam, right? And we can actually take and we can put not just the guy and the rock, but we can add, a little kid in the middle there somewhere, right? Or we could add a bucket of paint. We could add different things along the teeter-totter, and we could still be looking for the exact same thing, that is the tipping point or the balancing point. Okay, so I want you to actually have an experience to do that. Okay, so everybody's had an experience now of playing with kind of a two-dimensional representation, a one-dimensional, representation of what's going on, right? We've got these different objects along our beam, our ruler, and there's a center point, and it gets affected both by the weight of the object, or the mass of the object, right? And by how far it is away from wherever you've got your tipping point. So as you had a location, and then I asked every single one of you to move a piece of candy so you could see what happened, and it shifted where you had to do your center, right? Okay, so here's the way that this gets calculated. Again, this is not calculus. All right, we're getting to the calculus, I promise. But the way that this works in general for our moment is that our moment is calculated as each of the individual pieces of the candy, our mass, times its distance away from the fulcrum. So you've got mass 1 times distance 1, and you've got mass 2 times distance 2. And you keep going for all of the masses. We'll do it mass n times distance n at the end. Masses and distances being multiplied. And what we've been trying to find is a moment that's 0, where it's balanced. Does that make sense? Okay. So there's a couple more equations that we want to write in here. And this notation may not be familiar to you, so bear with me for a moment. You will see it again in Calc 3, those of you who are moving on to that later on. But this notation is what's going on here. This location, this balancing point, is found by taking the summation, that's the Greek letter sigma, from I equals 1 to n of the mass times the distance, those are subscripts of I, and dividing it by the summation from I equal 1 to n of the masses. Okay, so just jot them down. So what this is the top is this top is exactly the thing we calculated above. It's the moment. The bottom is the total masses of our objects. Not sure that's grammatically correct where it's written, but I'm not sure how else to write it, so we're going to go with it. Okay, so if you were to do this, and we had actually done a calculation with your ruler, right? What we would have to do is you could actually do it sort of from the end if you wanted to, and you could use the ruler piece along the edge. And you could say, okay, well, this one is like 1 centimeter from the end or 2 centimeters or whatever, and you could find each of those distances. We could weigh each one of our objects, agreed? And this would calculate, if I do all this on the top, when I did all of my masses times my distances, I'd get some number, and it'd be a positive number. Agreed? Distance is positive, and masses are positive. I'm going to get a big positive number, at least some positive number up here. The bottom is just the total of the masses. So it'd be like putting all of those pieces of candy on the scale at the same time and figuring out how much they weigh. Are you with me? That's the total mass of what's going on. And if we divide this, what we would actually find is how far away from the end of the ruler that our finger really needed to be to balance it. And it would give us the 19.8 that you were getting, or the 21.7, or whatever it would be. It would tell you, from a mathematical sense, exactly where that center should be to make it balanced. Can you picture it? Okay, good. Yeah, Tanner.
Why don't the masses cancel out? Since we're dividing by the masses in that summation, why do you need to multiply them in the first place?
So because the distance that they are away affects the force that it has on either side, right? Imagine if you're on the teeter-totter. If you do have somebody who's heavy and someone who's light, what you usually have to do is move somebody closer to the middle in order to get the balancing point. It's the heavier person that has to move. So the heavier person has to move closer to the middle to get that balancing point. And so the distance they are away from that fulcrum, that middle value or whatever, affects it. So what happens in my calculation, if you want to think about this sort of in a mathematical equation standpoint, is that we have mass 1, x1. I'll just do 3 of them so that I'm not writing them forever. Okay, so, and then I'm dividing by mass 1 plus mass 2 plus mass 3. So there's no canceling out because these are multiplication factors on top.
Yeah.
Okay?
Yeah.
Does that help?
Yeah.
Okay, we're going to do one. Now, I'd like for you to notice that these do have distances, x1, x2, x3, x4, x5, and some of them are negative. Okay? So if you want to imagine this is actually in, a grid where I've already got the center as 0 and I've got distances. So I've got, 0, 1, 2, 3, 4, 1, 2, 3, 4, negative. And so I've got different points along the way. There's one over here at -6, and it has some sort of a mass to it. We don't know. We've got, we do. It's above it. There's one at -4. There is a piece of candy, if you will, at -2. There's one right in the middle at 0, and then there's one over here at 8. Okay? So these are all of my candies. They look like some of the weight. In fact, y'all did it this way. You had one on one end and you had like almost everything else in the middle onto the other end, didn't you? Yeah. So these are the pieces of candy, and they all have, or at least potentially have, different weights. And the problem is set up to tell you right above them what the weights are. So this one right here, right, the masses, at x equal -6, the mass is actually 12. And at x equal -4, the mass is actually 1, and so on. Okay? So there's two things in general that you have to calculate. You have to calculate the moment, which is each of the masses times the distances. So you have 12 times -6 plus 1 times -4 plus 6 times -2. We have 3 times 0, not very exciting. Did I miss one? I don't think so. And then I have 11 times 8. Okay? I'm not going to find this amount right now. Just pause. We'll get there. But the other thing we would, in general, have to calculate is the total mass, which is just each of the masses added up. So you have 12, 1, 6, 3, and 11. Does that make sense? One of these, the first one is the numerator for x bar. The other one's the denominator for x bar. So take a calculator real quick. Let's find both of these. Something kind of interesting is going to happen. But it sort of makes it look like it always happens, then it doesn't. So it's just this problem. What happens on the first one for the moment? What do you get? It is 0. So in this sense, we don't really need to do the denominator. We're going to just because in general we would. But we should take the moment, which is 0, and divide it by the mass. What's my total mass? 33. I got 33. 33? Okay, yeah, okay, cool. Okay, so in general, it wouldn't be 0 divided by 33. It'd be something else. This one is 0. This is telling you that if you put all the objects on there with all of these masses as described, the tipping point would be at 0. Agreed? And you guys found that to happen on one of yours, right? Where one of them was kind of in the center and everything else was on one side, but one of them was far enough over, because this is a pretty far away distance, to have a big enough impact, and it was a heavy one. It's 11 compared to the other ones. The only other one that's close is actually the 12. So this one is finding this in 2 dimensions with multiple objects. Okay, I keep saying 2 dimensions, 1 dimension with multiple objects. Now we're going to do 2 dimensions. Are you ready? Everybody needs to come forward, and you need to get a plane. Okay, so come back, get your candies. You need one of these. There's actually a grid on it on one side. There's really not a value for us for what we're doing necessarily, but just to have a picture of it's fine. And you're going to do the same thing. You're going to take the candies, 4, 5, 6 of them, whatever you want, put them in different places all along the grid, and you're going to try and do exactly what Tanner's doing, which is to balance the square now instead of just the line. Are you with me? And you can technically do it with just one of them on there, too. It's a little harder. They're balancing better if you put more than one on, actually.
That's good.
Well, that's fun. Thank you.
No problem. Okay, so you've had an experience now where you have moved these around in 2 dimensions. I do actually mean 2 dimensions now. So this is imagining balancing an object, which you don't have to imagine. You just did it on a 2-dimensional shape, i.e. 2 blocks on a plate, or you did candies on kind of a square slab, right? We're still looking for the point where your object with the masses will be balanced. There's going to be balance in there. So has anybody seen the National Treasure movies?
Yes. Yeah.
Okay, they're a lot of fun. If you haven't seen them, I mean, I'm sure there's probably inappropriate stuff in it, because that's what happens every time I say something like that, and I go back and watch it, and I'm like, oh, I remember that part.
Yeah.
Usually happens in the middle of trying to show into a bunch of children. And I'm like, oh, let's move forward. Anyway, they're really fun movies. And so I can't find like a clip of the movie without buying the whole movie. So I've got a trailer, and we're just going to try to move forward to a part of the trailer. This is National Treasure 2. And there's a point in the movie where they're trying to do exactly what you did, but they're not doing it with candy. So I'll pause this. Okay, so real life applications, sort of, right? We have Nicolas Cage, and I don't remember the actress with this name, but they're trying to balance themselves on a rectangular slab or square slab and not die, right? They're not trying not to die. So, yeah. And so we're going to take a look at how we calculate this in 2 dimensions, because we've only done 1 dimension. We did 1 dimension with a single object, then we did 1 dimension with several objects. We did 5. Now we're going to do this in 2 dimensions, like your rectangular slab or your square slab, right? This one and your candies. And if you'll notice, the formulas look a little the same, right? It says m sub y, and it has masses and distances. And it says m sub x, and it has masses and its distances. And then our center of mass down here is found, again, by looking at the moments divided by the total of the masses all along the way. So go ahead and jot those down. There is one nuance to that I'll mention, but I just wanted you to write it down first so that we can pay close attention to what that nuance is. Okay, what's the difference or the maybe odd feature in these formulas? Did you notice it when you write it down?
Moment about the y-axis uses the x values.
Yes, the moment about the y-axis uses the x values, and the moment about the x-axis uses the y values. Not only that, so you see it written both down here, right? Right, x bar has m sub y, but look back up at the equation for m sub y. What was in m sub y? X's, right? Okay, so pay attention, be careful, you put their pieces in the right places, all right? So we're going to do an example for this. Did everybody get it all written in? Sorry, I will slow down a little. Okay, are we good? All right. So we're given like a table of values. Each of our objects has a mass, just like your candies would have, and they have a location in the xy coordinate plane. And we're trying to find the center, just like you were doing with the candies on the plate. It's exactly the same thing. So we're going to take and we're going to work with each one of these. So we're going to find m sub x, and we're going to find m sub y. And then we're going to end up finding, we need the mass as well, so we'll find that too. We'll find m for mass. And then in that, we'll find x bar and y bar. These are the quantities we're going to find. The answer of what we're actually trying to find is x bar, y bar. Like our answer at the end needs to say x bar, y bar equals. This is the setup of what we're doing. Everybody good? Okay, so in each one of these cases, the mass values are going, the first 3, the mass values are going to show up. So 12, 6, 4.5, and 15. So with m sub x, we have 12 times what? 3. It's the y values that get multiplied when we do m sub x. Good. And then I have 6 times 5, and 4.5 times 8, and 15 times negative 2. Okay, so in m sub x, I'm using y values. So somebody find that for us with calculator real quick so we're not spending too much time multiplying and so forth. Too big.
Oh, I've got the negative. 72.
72 is right. Okay, we're going to do the same thing now with the x values for m sub y. So I have 12 times 2. I have 6 times negative 1. I have 4.5 times 6. And then I have 15 times 2. going to be really close to 72, but it's not 72. 75 is it. Good job, Piers. So we have 72, we have 75. What do I do to find M?
You add the masses.
You add all the masses up. So we have 12, 6, 4.5, and 15. Gives me a total of?
37.5.
It's 37.5. Now, when I come down here to find X bar and Y bar, remember that X bar goes back to which value? M sub Y. So this one goes back to M sub Y, the location where I put all the X's in. So it will end up giving me the 75 divided by 37.5. What is that value? That is just 2. It's a nice whole number. The other one's not going to be. And then our Y value will go back up to, our Y bar will go back up to M sub X. So it's 72 divided by 37.5. What's that one give me? It's almost 2. 1.92. So the location, if you were doing this on the thing, right, and you saw the grid on one side of it and there was not a grid on the other, so if there's a grid on one side, your location in space would be an X coordinate of 2 and a Y coordinate of, well, almost 2, 1.92. Okay, but this still isn't calculus, is it? Okay, so do you remember back to the very beginning of Calc 1 when we kept looking at things that were like, this is pre-calc, this is calc? Remember that very first lesson? Except for Preston didn't have that one, but maybe you had a very similar experience, I hope so. This is pre-calc, this is calc, this is pre-calc, this is calc. Everything you've done in class today, physically, and everything we've written have been done on a very rigid shape, right? It was a plank, or the ruler. It was the square, right? It was a very specific shape. What we're going to do then is make the shape arbitrary now. We're going to have what's called a planar lamina. So we're going to consider a thin, flat plate of material of constant density. Okay, so it's not going to vary in the density. So this is not the pottery that somebody makes where it's thicker in one place and thinner in another. That's not what we're looking at. So it's very much like these. It's just that it's not a rigid square. Can you picture that? Every point on this, because it was made in some sort of factory, it's got constant density throughout. Are you with me? Okay. That density, or that constant, let's see, where was I? Planar lamina. Density is a measure of mass per unit volume. For a lamina, it is mass per unit of area, notated rho. That's a Greek letter rho. It looks kind of like a lowercase scripty kind of p. For an irregular shaped planar lamina. So imagine taking one of these now and cutting it into some weird shape. Right? It looks like a pond now. It doesn't look like a square. It looks like a pond. It's got some sort of irregular shape, some circular features, some curving, maybe some straight line segment edges too, but it's an irregular shape. Then, in order to find the mass of that, we would take the integral from a to b of f of x minus g of x dx, which is rho times the area. That's a formula, this part of it, that you've seen before. Where did we see that show up? Area between two curves, right? 7.1. It's the very first section that we talked about. This is finding the space of the bounding lines or curves of a trapped piece of area. Now, there's more formulas to be had because we had m sub x and m sub y, and now they look kind of crazy. So, center of mass for a planar lamina. If you're writing everything down and you didn't print anything out, you might want to take a picture of this one because there's a lot of writing on this one. We have our continuous functions. We are going to say that f of x is bigger than g of x. And we have this constant density business. Our equations are y equals f of x, y equals g of x. Our integral goes from a to b in all the cases. Those are my limits of integration on x. And what you see is a few different formulas. If you wish, another way of writing this formula would be to move the 2 out in front. And then you could write it without a 2 underneath there. Your choice on that. But this is the average, like f of x plus g of x divided by 2 would be the average value of my two curves. F of x minus g of x, that's the trapped area part of it, right? That's where that's coming from. That's with m sub x. And then for m sub y, I have x times that trapped area form. Now, center of mass down here looks exactly the same as my previous slide, right? X bar is m sub y over m, y bar is m sub x over m. And then now I have that same, this came on the previous slide, the formula for finding mass. So the formula for finding the mass, which is the same as the area, right? It's the area of my shape. This is going to be the integral from a to b of f of x minus g of x. And that should have a dx on the end of it. That's definitely left off. That should say dx. And now you see calculus, don't you? Yep, we see calculus everywhere in this problem. Now, here's your warning. These problems are lengthy. This is my last sheet. Okay?
It's one problem?
It's one problem. It is one problem. But think about what you're finding. You're finding 3 different integrals, correct? So does it make sense that it should take some space? Probably, because I'm finding 3 different integrals. It's like 3 problems in one, kind of. All right, so let's take a look at one. If you want to come back and take a snapshot of this, or if you want a snapshot of this, do you want to take a picture or anything real quick, Sophia? You get it later. You got everything? Okay, cool. All right. So we have a question asking us to find m sub x, m sub y, and then the center of gravity, x bar, y bar. Okay? For landlemmas of uniform density rho, they're bounded by y equals negative x squared plus 4x plus 2, and y equals x plus 2. So I've got 2 equations, just like I've had in a variety of contexts all throughout chapter 7. And the first thing I need to do is to look at a graph or calculate it by hand if it's something that's straightforward enough you want to do it that way, to figure out what the bounded area looks like. Okay, so grab a calculator, and I'd like for you to put in the equations y equals negative x squared plus 4x plus 2, and y equals x plus 2. So the first one's a parabola, the second one's a line, and the line might look something like that. And my parabola looks something like this. So do you see trapped area? Sure. We see an area being trapped by 2 curves. This one right here is the y equals negative x squared plus 4x plus 2. Okay, so as we're taking a look at this and we're doing subtraction, we're always going to be subtracting f of x minus g of x. It's going to be the parabola minus the line, because we see that that's what's on top versus on bottom. Make sense? So we need the graph to be able to determine which one's on top and which one's on bottom. You could use absolute values if you wanted to. We did that back in section 1, but they kind of end up being a little bit messy sometimes too. So if it's easy enough to determine it, which it's not too bad, probably the better way to do it is that way. Okay, so we're going to take a look at finding m sub x, m sub y, and m. So m sub x is probably the hardest of the 3, excuse me. So we're going to start with that one. So if we do, in fact, get cut short on time, which I don't think we will, you'll at least see the hardest one, okay? So our formula actually had a rho and an over 2 in it, which I told you I could pull the 2 to the front, so I'm going to. And then our integral, I need to know my limits of integration. I need to know this location, and I need to know this location in terms of my x values. So what's the first x value? Clearly 0. That one's an easy one to see. How are we going to find the second x value? There's more than one way to do it. You can ask the calculator to find it for you, sure. There's actually an intersect feature in your calculator if you want to use that. That's fine. You can trace over there and make a pretty good educated guess. Or you can calculate it by hand by setting the 2 pieces equal to each other and solving. Yes? It's a good question. Let me find it.
Second trace. Yeah, so calc.
Yeah, there's the calc menu. The second trace menu is a calc menu.
Oh, I see it.
And it says intersect. The one caveat to it that you need to be aware of is that you need to be close to whichever point you care about, because it's just going to find whichever one's the intersection that's nearest to the point you're at right now. So if you want to make sure you're finding my second one, the one that's on the farther right, just scroll over there a little bit to it. What is the intersection point over there for x?
3.
It's 3. Okay, now the formula over here says that I'm going to need to find the sum of my two functions and the difference of my two functions, correct? So that's what I'm doing next. So I've got the sum of my two functions, which is negative x squared plus 4x plus 2 plus x plus 2. And then the other one, which I'm now out of space for, so I need to do some shifting around, is going to be negative x squared plus 4x plus 2, and it's technically minus x plus 2. So I'm going to write it in embedded parentheses for the moment, and we'll distribute the negative in a sec. There's good and there's bad here. The good is we do have a polynomial. So finding the antiderivative of this in a little bit is going to be not too bad. The bad is it's really messy right now, and we're going to have to do a fair bit of distribution in order to get to the point where we can do that. Okay, good and bad. So let's clean some things up and go from there. So inside the first set of parentheses, I have negative x squared plus 5x plus 4. Does that look right? The next one I have negative x squared, and if I distribute this negative through, I will have plus 3x, and then the 2's are going to cancel, dx. Okay. Admittedly, it's not great, but it's better looking than it was before. Agreed? Okay, so you remember from algebra that in order to do this, we're going to have to distribute everything in the first set of parentheses to everything in the second. So whatever it takes for you to keep those straight, do it your way, that's fine. I'm going to show you how I do that to keep it straight for me, but if you like something different, then by all means do so. I take the first value and I distribute it. So I'm going to do it that way. So the first part's going to remain the same. We have rho over 2 integral from 0 to 2, and I'm going to distribute my negative x squared through, so I'm going to have...
0 to 3.
Yeah, 0 to
Oh,
3.
I keep changing it. Thank you. Cut. 3. Thank you. So negative x squared times negative x squared would be x to the 4th. And then negative x squared times 3x would be negative 3x cubed. Is that okay? Good. And then I'm going to go to the next one. So I'm going to distribute my 5x through. So my 5x times my negative x squared would be negative 5x cubed. And then my 5x times my 3x would be positive 15x squared. And then we're going to distribute the 4 through. So 4 times negative x would be negative 4x squared. Negative x squared, I mean. And then 4 times 3x would be plus 12x. Okay, so some computational algebra kind of stuff. We're going to combine some like terms. So I only have an x to the 4th. How many x cubes do I have? Yep, negative 8x cubed. How about my x squareds? 11? 11x squared, and then 12x at the end. Okay, integration. Okay, so we did the messy part. Now we're doing the part that's at least friendly in terms of like how do we integrate, right? There's no u substitutions or anything like that going on. It's very straightforward. So we're going to do the integral, or the rho over 2. Sorry, no integral right now. What is x to the 4th derivative, antiderivative, excuse me? Good, x to the 5th over 5. Then I have negative 8x cubed, which would give me negative 2x to the 4th, right? Because I'd be dividing by 4. How about 11x squared? That's ugly, right? Yeah, so 11 thirds x cubed, or 11x cubed over 3. And then how about my 12x? 6x squared. And we're going to be evaluating that at 3 and 0. But the nice thing is that what happens when I evaluate with 0? It gives you 0. So again, we do have another friendly feature going on. I'm going to use my next screen. We'll finish this piece up. Feels large. Okay, so we're going to evaluate. I recognize, and you should recognize too, rho will be a part of our answer. Don't worry about it. It's going to disappear eventually, but not right now. So rho over 2. So we have 3 to the 5th over 5 minus 2 times 5 to the 4th plus 11 thirds.
395.
Oh my goodness. Thank you. 2 times 3 to the 4th, 11 thirds times 3 cubed, and then 6 times 3 squared. And then all of that is technically got minus 0 at the end for evaluation of 0. Okay, so leave the rho and 2 out of it for the moment. What do you get inside the brackets? Decimal will work just fine here. You can put it in fraction if you wish. Either way will be fine because I don't have a repeating kind of version of anything or anything irrational. So what's it become? Okay, and those are both what I have too. So you have, I'm going to go with the decimal, 39.6 you said. If you want to write it as the fraction, that's fine too. And then because I've got a division by 2 for my rho, I'll divide that by 2. And what would that be? What's that?
What's the fraction form again?
Oh, what did you have, Tanner?
198 over 5.
Rho over 2, 198 over 5. So if you've got this one, you're going to have, what is 198 divided by 2? 99. 99 rho over 5 if you're doing it in fractions, or it's 19.8 rho if you do it in decimals. And this was m sub x. Okay, is that okay? Let's do m sub y. So m sub y is a little bit shorter than the last one. It's rho times the integral. Still 0 to 3, so we get all of that. We don't have to work for it again. And then it's x times f of x minus g of x. And if you wish to find f of x minus g of x, you may, but we've done it already. It was right here, and it reduced to this. So this negative x squared plus 3 is what we're going to end up with. Just in case you want to be able to look back at this later and remember where you got that, I'll write it in. But you could just jump to that, and it would be okay as well. Negative x squared plus 4x plus 2 minus x minus plus 2, which will be minus 2 when you get it in there. So this is rho integral from 0 to 3 of x times negative x squared plus 3x dx. We'll distribute our x through. So it's negative x cubed plus 3x squared dx. What is the antiderivative of negative x cubed? Yep, negative x to the 4th over 4. And the antiderivative of 3x squared? X cubed. Evaluating at 3 down to 0. Okay, so we'll plug in 3. So we're going to have negative 3 to the 4th over 4 plus 3 cubed. And then once again, we have minus 0 at the end for evaluation at 0. If in the case of these zeros, you left these zeros off, I'd be okay with that. Just don't leave it off if it doesn't end up being 0. That would be bad. All right, so when we simplify this, we're going to get, let's see, where's my answer in there? 6.75 rho. Or if you want to write it in fractions, you're going to get 27 rho over 4. Okay, our last thing to find is mass. Do I have space? I do. So we'll do it on the next slide. So the mass is actually rho times the integral from 0 to 3. And it's just supposed to be f of x minus g of x. So negative x squared plus 4x plus 2 minus the x minus x plus 2 dx. So this is rho. It's the integral from 0 to 3 of just the same thing we've been getting all the way along, negative x squared plus 3x. Okay, no x at the beginning because I don't have that for the mass. So this would be negative x cubed over 3 and 3x squared over 2. Evaluated at 3 and 0. So my rho will give me, my rho will be multiplied by negative 3 cubed over 3 plus 3 times 3 squared over 2. And all of that subtracts the 0 off at the end. And this one ends up giving me, where's my value at the end? 4.5 rho, or you can do 9 rho over 2. So we've found two of the things we were asked to find, which was m sub x and m sub y. We found m because we also are asked to find x bar, y bar. So x bar and y bar. So x bar means taking m sub y. M sub y was my 6.75, I'm going to do mine in decimals, 6.75 rho, and then dividing it by the mass, which is 4.5 rho. For y bar, I'm taking the x, or the m sub x, which was 19.8 rho, and dividing it also by the 4.5 rho. And what happens to rho? They cancel. Okay, so it's constant density, but it doesn't matter what the density is. It does not change our center of gravity. Okay? So then, when we divide these, we end up getting that my x bar is actually 1.5, the y bar is actually 4.4. So my x bar, y bar is 1.5 and 4.4. Okay? Okay, I have one example left to do. I will start it, and then I will post the video for the rest of it. And I knew I was probably forfeiting the ability to get finished, but I felt like that the experience that we had with the rulers and everything was worth the time, and I hope you felt like it was too. So centroid is the last thing to talk about. The centroid is the center of mass of a region with constant density where rho is equal to 1. So we would calculate x bar, y bar with rho is equal to 1, but we found out last time that it really doesn't matter what rho is. It cancels out anyway, right? So in a very real sense, we're doing all this calculation. We just aren't going to have a rho in it when we're finding our answer at the end, okay? Because they cancel out anyway, okay? So a centroid specifically is a planar lamina with a density, a constant density where it's equal to 1. All right, so this object is a little bit different than the ones we normally see. What I want you to recognize is that while you see lots of letters, there's only one variable on the right-hand side. The variable is x, okay? A and B are just numbers. We just don't know what they are, but they're numbers. They're constants. So when we think about finding antiderivatives and derivatives, those are constant values, just like if you had the number 5, okay? So we're going to find the image first of this shape. And you might be thinking, well, how do I find the image of it when I don't know what the A and the B are? This is an object that's at least somewhat familiar to you, or at least similar to something that is familiar to you. If we were to solve this for the values, change the expression, let's say. So I would actually be multiplying to get rid of my denominator. So this would be ay is equal to b square root of a squared minus x squared. And if I squared both sides, I'd get a squared y squared equals b squared. And then I'd have a squared minus x squared. And I know that looks really messy, but just bear with me. It's going to clean up in just a second, and it's going to be something that you have seen or have almost seen before. So let's see, I've got a squared y squared. Well, I'm going to write my a first. A squared b squared, and then b squared x squared. That was supposed to be a subtraction sign. And if I move my bx squared over here, this is b squared x squared plus a squared y squared equals a squared b squared. Okay, so you may not like the way that this looks, but for a moment, imagine that these aren't here. They're all equal to 1. What would that look like? It's a circle, right? It's a circle. But that's assuming that both A and B are equal to 1, and A and B don't have to be the same. Like one of them could be 1 and the other one could be 3. So what this actually is not quite a circle, but it's what we call an ellipse. Have you heard of ellipses before? Okay, and again, we go further into ellipses in chapter, I don't remember what it is, chapter 10 I think it is, it's in Calc 3. So we talk more about ellipses and hyperbolas and parabolas and stuff there too. But the image that this gives us looks something like this. It kind of looks like a circle, but it's flatter. And the distance out here and the distance up here are not the same because it's not a circle. So the distance to the top is B and the distance to the sides are A and then negative A based on how this is drawn. Okay, so this is our planar lamina. That's the object that we're working with right here. Okay? And so we're going to find m sub x and we're going to find m sub y and we're going to find the m value. There's also going to be a point in the video that I post that talks about the fact that we could have just found this quarter of it if we wanted to, this half of it, because there's symmetry. So we could go from 0 out to b instead of going from negative b to b. And it might be preferable to do so because we really like plugging zeros in at the end, right? We do. They're friendly. The one thing that's not so friendly is remember where this actually started. This actually started up here where I've got square roots. But that's actually a good thing because what happens is that you're not expected to do it by hand. Your calculator is going to help you with this problem. And I'll talk in the video that I post about that. So I am going to post a video. The video is from a long time ago. I promise I would be saying the same things, okay? But I'm not re-recording something when there's a video out there that's just going to do it for you anyway. I'll tell you where in the video to start. It's going to be the last probably 7 or 8 minutes. It's not very long. And that will be what you'll want to watch before you finish the rest of the section, okay?